Hello, everyone. Come on in. Step right up. Step right up. I actually have a lot of hair. This light is just pretending like I'm bald. That's the truth, honestly, really seriously. I did get my haircut today, but dang, this light's really making me look balder than I normally look. Woo, look at that. Oh, well. That's my mark. I earned the baldness. Anybody have any questions before we get started, folks? All right. Well, I guess I'll go ahead and get started. The time's actually up. We're finishing up chapter 30 today. And in principle, we're going to start chapter 31 next, but I don't really have enough time to get jumping into that, but I'm probably only going to spend one day on it. So Monday of next week, we'll probably cover all of chapter 31, which means in order for me to really be able to do that, you guys probably need to go ahead and read chapter 31 a priori. So I want you to focus on electromagnetic waves. I want you to focus on the Poynting vector and what it is, what it means, what's this formula, and how the electric field and magnetic field are related to one another. That's the sort of what I consider the most critical aspects. And then I want you to consider electromagnetic radiation, which is basically the waves that you can get by combining Maxwell's equations. So if you assume there's no source of current, which would be the J, and if you assume there's no source for electric field, which would be the rho, but you still have the other ones that a magnetic field can beget, a changing magnetic field can beget an electric field, and a changing flux can beget a current, then you will be able to basically set up the equations of Maxwell's that can be used such that you ultimately get a wave equation. Now, I've worked that out on my YouTube channel, so by all means, check it out. It's a little bit beyond what this course is supposed to be able to do, but I don't think it's that hard to follow. It's just some simple mathematics. It's not that big a deal. But the main thing is, what you'll find is that next semester, or excuse me, next chapter, what you'll find is that there's something called electromagnetic radiation. And the parts of that electromagnetic spectrum, I use the mnemonic to remember, and it's great excess undermines various industries' Marxism rules. So that's me paying homage, if you will, to Rush Limbaugh, who always talked about us teachers being commies. So, and I'm a big, Rush Limbaugh fan. I've been listening to him since '89. I don't agree with him 90% of the stuff that he talks about or talked about before he passed away, but still, I like to make that little mnemonic to help you remember the parts of the electromagnetic spectrum. So great, as in gamma rays, excess, which is spelled with an X, so that means X-rays, undermines, which is ultraviolet, various, which is visible, industries, which is infrared, Marxism, which is microwave, rules, which is radio waves. Okay, so that's the parts of the electromagnetic spectrum. That's a very specific order. That's from short wavelength and high energy to long wavelength and low energy. It's also from high temperature to low temperature is another way of looking at that. So that's the parts of the electromagnetic spectrum. And that with what electromagnetic radiation is the crux of it. So basically, it turns out that there happens to be an electric field oscillating, and let's say vertical, and the direction that it oscillates is called the polarization of the electromagnetic radiation. And then perpendicular to that electric field is a magnetic field that's oscillating perpendicular to that, like this. Now, if you happen to notice which direction it's moving, come to find out that direction of that propagating electromagnetic radiation is in fact in a third mutually perpendicular direction. And it's such that E, which is up and down, cross B, which is, well, I'm saying up for right now. So up is E. I'm saying to the right is the magnetic field. My right, not necessarily yours. So if I curl my fingers towards B with a right hand rule, then my thumb points that way, which is the direction the wave's going. So if the electromagnetic field was up and if the electric field was up, at the same time, the magnetic field was propagated all the way vertically to the right, or horizontally to the right, then the electromagnetic wave would be coming towards you like that, okay? And that actually helps you remember the pointing vector, which is basically like 1 over mu times E cross B, okay? So that's what we're doing. And like I said, I want you to have read chapter 31 before you come to class on Monday, and we're gonna go ahead and finish chapter 30. Makita said we had a video to remember that back in like middle school. Yeah, that's always helpful. Also remember there's the Roy G. Biv for the visible part of the spectrum, but that's in exactly the opposite order as my great excess undermines various industries Marxism rules. That has to be Vibgyor if you're wanting to remember the visible part of the spectrum in the same order as great excess undermines various industries Marxism rules. So anyways, when we last spoke, I just finished handling an LC circuit, which is really a theoretical construct that you can approach as close to it as you want. In other words, if you, let's say, are willing to make the resistance 1/1000th of a ohm, then you can probably get an LC circuit oscillating with no loss for a good period of time. Of course, that's going to take some work to get 1/1000th of an ohm, but in principle, there's no reason why you can't, other than physics. So what we did with that, though, is I worked out, or I plotted the energy because I didn't really have time. So I wanted to go ahead and plot state what that energy is, because what we had found was a harmonic oscillator equation for the LC circuit without resistance. And from looking at it by its form, we knew from chapters 14 and 15 exactly what form the solution would be, and it'd be of the form Q equals Q0 cosine parentheses omega t plus phi, where phi is a phase angle and Q0 is another another constant of integration, just like the phi is. Okay, so when you're dealing with a second order differential equation, you actually need 2 data points. You could have like x at t equals 0, and then you could have like x at t equal 5, or you could have x at t equals 0 and you had dx dt at t equals 0. You just need 2 equations so you can get rid of the 2 constants of integration. That's really what you're doing when you're solving a differential equation. In some senses, you're just integrating. If it's a single order differential equation, meaning it's only got a first order derivative, then if you integrated a first order derivative, you're going to get an answer, but it will have 1 constant of integration. But if you do that to a second order differential equation, you're going to have 2. So that's what we're talking about with regards to that. So let me start off by recapping the end result. Specifically, what I want to do is I'm going to show you the energy stored in the electric field, and then I'm going to show you the energy stored in the magnetic field, and remind you what the graph of energy versus time is. And that's the first instance where you get to see that the electromotive force, i.e. the voltage, leads the current in an inductor. Okay, that's Eli from Eli the Iceman. So let me turn on the document cam. Does anybody have any questions before I start? Okay, looks like we're all good then. All right, so first off, we have basically the energy stored in the electric field. So the energy stored in the electric field, U sub E, if you remember from our capacitance days, is 1/2 Q squared over C, but we also had that Q is equal to Q0 cosine omega t plus phi. So when you plug that in, you're going to find that the energy stored in the electric field is, of course, Q0 squared over 2C, and that times cosine squared omega t plus phi. So that's the energy stored in the electric field, specifically because the electric field is the field that the actual capacitor has in it. let me get a little better focus on that. It looks a little blurry. Okay. Now the electric or the energy stored in the magnetic field at any point in time, notice this is a function of time, is given by 1/2 Li squared. And again, in this case, I is equal to negative dq dt, which if we take the derivative of that, you see the derivative of cosine is negative sine, but putting a negative in front of it is going to make it positive. So it'll be positive omega q0 sine omega t plus phi. And that's that. Okay. Now, if we plug all that into here, we get UB, the energy stored in the magnetic field, is going to be equal to 1/2 Li squared. So what we end up getting is L omega squared Q0 squared over 2 times sine squared omega t plus phi. And this is what I actually graphed. Since it's squared, it's never going to go negative, of course. And if you make a plot versus time of the energy, I'll put E comma B like that. Then the electric field goes like cosine. So it'll be like this. Like that. And of course, the magnetic field goes like sine. So that'll be like this. So this green is U sub B, and this black is U sub E. Okay. So what I was saying is, remember, the energy in a capacitor is 1/2 CV squared. So another way of looking at it, instead of using that equation, I can use Q equals CV to get 1/2 U is equal to 1/2 CV squared. And I can realize that the other one is 1/2 Li squared. So we see that the energy is a maximum in the capacitor when the voltage is a maximum, but the energy is a maximum in the solenoid when, or the inductor, when the current is a maximum. So in this case, if you think about a actual inductor, you'd say, oh, well, it appears that the current in the inductor is a maximum sometime after the voltage is a maximum, and we reach the conclusion that Eli is right. Then that means the voltage leads the current in an inductor. So that's a way of saying it's a little more complicated, because you sort of got to think about which energy is which and what's going on with the other part, even though this is just a graph basically of the energy stored in the inductor, whereas this is a graph of the energy stored in the capacitor. So it takes a couple separations from first order considerations before you can make this jump from that. But you'll see another chance in a second. So now that we've gotten that established, I wanted to work an example using what we learned, specifically using the fact that Q is equal to Q0 cosine omega t for our LC circuit. So when you have an LC circuit, remember that just turns out to be an oscillatory circuit where the energy sloshes back and forth, not unlike the kinetic energy and the potential energy of a mass on a spring. The mass on the spring goes to its negative spot at exactly the same instant that the potential energy of the spring is a maximum. Okay, it's a maximum in the sense that it's stretched to its fullest. And then the kinetic energy becomes a maximum as it goes through the zero of the spring. In other words, the equilibrium position of the spring. So the kinetic or the potential energy of the spring there is zero. So they're sloshing back and forth. The same thing's happening with the energy in the capacitor versus the inductor. So here's example 1. So what I'm going to say is, let's imagine we have a 2000, and I'm going to put 0.0 there so we can make sure we know at least 3 sig figs are there. In fact, I've forced myself to make 5 sig figs. I didn't necessarily want to, but I wanted to use 2000. Let's say we have a 2000 picofarad capacitor, And when I call it a 2000 picofarad, I have to actually put a hyphen between that. That's just grammar. Okay. If I said it has a capacitance of 2000 picofarads, the hyphen wouldn't be there. But I said it's a 2000 picofarad capacitor, so I had to put that there. And or excuse me, I said inductor. That's supposed to be my capacitance. Sorry. So that is the capacitor's capacitance. We should have known that because I said Faradays instead of Henrys. Anyways, so that's the capacitance of the capacitor is 2000 picofarads. We're going to fully charge that at V equals 400.0 volts. Again, I'm putting this just so that I want to make sure I get at least 3 sig figs. So I had to put a dot there at least with my rules for sig figs. And then I'm going to charge it up and then disconnect it and then reconnect that circuit to a 100 millihenry capacitor or inductor, excuse me. So L equals 100.0 millihenries. If I called that a 100 millihenry conductor, then I'd have to write it as 100.0 hyphen millihenry. And I'm about 99% sure that's hyphen, not dash. Okay. So anyways, that's what's going to happen. And that's going to happen at t equals 0. Now, what I want to find out is what is the initial charge of the capacitor? In other words, when I take this capacitor and connect it with that 400 volt power source, DC power source, what charge is the capacitor going to get? So that's a pretty straightforward problem. Then part B, I'm going to ask you for the period and the frequency. So I'm going to say T equals question mark and F equals question mark for the oscillating circuit. Because when you have a charged capacitor and you connect it in series with an inductor, the energy, like I said, is going to slosh from back and forth between the capacitor and the inductor, capacitor, inductor, capacitor, inductor, capacitor, inductor. So I want to know what's that frequency and period of oscillation. Part C, I would like to know the max current. So I'm just going to call that I max equals question mark. And then part D, I'm going to ask the total energy. So U total. And if you look, there's a derivation in your book that gives you exactly that formula. You can actually get it another way too. But the one they give you in the book is basically that it is 1/2, or excuse me, Q0 squared over 2C. So that's fine. But as you can tell, it could also be the max current times 1/2 Li squared. That would be another expression you could use. Okay. So let's first off start by writing out the solution to A. So our circuit, by the way, is initially this capacitance with a charge Q0 has been put in series with an inductor of inductance L. So I first want to know A, Q0. Well, according to C equals Q over V, that means Q0 should equal 2000.0 picofarads, which by the way is times 10 to the negative 12th, times the voltage, and the voltage is 400.0 volts. So you can see I'm getting like 4 sig figs for all this junk. I'm going to compute this, but I got to remind myself to tell you something after that. Okay, so let's see. So I'm going to take 2000, 000, e to the negative 12 times 400. And that's going to give me 8.000. Technically, it's 4, so it's 4 decimal places. So that's 8.000 times 10 to the negative 7th coulombs. Now, that's the charge. You could also write this, for instance, if I divided this by 100, that would become 10 to the negative 9th, but I have to multiply that by 100. So that'd be 800.00 nanocoulombs is also acceptable. Okay. Now, what I want to say about this, well, last time I did a calculation with an inductor and I got like 898 Henrys. Check that math because I think I'm off. It was supposed to be actually 0.0000 898 instead of 898. Okay, so just check that in last class's meetings. I did not make the correction on the notes before I posted them, so there's still error, but you guys should be doing these calculations as I'm doing them so that you can actually catch me making any mistakes. All right, so we now have the charge that this thing will have after we disconnect it from the 400 volt source. Now what I want to figure out is what is the period and frequency? Well, we know that frequency can be found from omega, and omega is equal to 1 over the square root of LC, like that. So what I want to do is I'm going to take L times C and raise it to the -1/2 power. So L, of course, is 100.0 millihenries, and of course milli means times 10 to the -3, and I want to multiply that by 2000 times 10 to the -12 farads, and then I'm going to raise that to the -1/2 power, and that should give me my answer. So I'm going to put this in my calculator, and I'll maybe even show it so you can make sure I don't make any mistakes. So I'm going to say 100 e to the -3 times 2000 e to the -12, and that's just the part we multiplied. Now I'm going to raise that to the -1/2 power, so I'll put -0.5, and that gives me 70,710. .7. Then that's radians per second, or just per second. So another way, you could just call it S to the -1. Now, actually, I had 1, 2, 3, 4, 5 sig figs, and I had 4 here. So 1, 2, 3, 4. This guy and this guy, extra digits. Now that's omega. What we really want though is F. So the frequency F is given by omega equals 2 pi times F. So what we see is F is equal to omega over 2 pi. So I'm going to divide that number by 2 pi. I'll put a parentheses around it, because if you don't, it's going to divide by 2 and then multiply by pi. So 2 times 3.14159. And there is a pi key, but it takes longer for me to punch it, so I'm not going to do that. So that's 11,254 hertz, which, using proper sig figs, that should be 1.12, that's 5 times 10 to the 4th hertz, or it could be 11.125 kilohertz. So that should be right either way. Hopefully someone's verifying their calculations on that side. Anybody got any problems with the answers I come up with so far? Now the period is actually just 1 over the frequency. Did I hear somebody getting ready to say something? So the period is 1 over frequency. So I'm going to do 1 divided by, and I'm going to call it the last answer I did, and that gives me 0.000089. So that's 0.0000890, or that'd be 8.9 times 10 to the -345. I like this number better than the one I got earlier. Hopefully this is the right one. We could also, of course, multiply this by 100, and that would make it 10 to the -3rd, and then divide that one by 100, and we get 0.089. That'd be 1, 2, yeah, 89 milliseconds. Or we could divide this by 10 and multiply this by 10, and it'd be 89.00 microseconds. So both of those are actual real answers that could happen. Sorry, I realized now that my writing went out the screen when I was trying to write that. So now we have the period and the frequency of the circuit, and that just means the circuit's going to oscillate back and forth, like we said, but it's going to oscillate with a frequency of 11.25 kilohertz, and it's going to have a period of 89 microseconds. Part C, I wanted to know what was I max. Well, if you remember correctly, when I took the derivative of Q with respect to T, the negative of it gave me the actual current. Of course, what it was saying is the current is wobbling back and forth between basically this quantity and the negative of this quantity. So that tells us that, in fact, this should have been Q0. That tells us that omega times Q0 is actually I max. So I'm going to write I max is equal to omega times Q0. So what we found omega to be was 70,710.7 radians per second. And then what we found Q0 to be was 8.0000 times 10 to the negative 7 coulombs. So this will give us coulombs per second, which is exactly a measure of an amp. So let's see if we can calculate that now. So my number is going to be 7. Actually, I'll go up and grab that number. And then I'll multiply that number times the one I got earlier, which was 8 times 10 to the negative 7, which is that number. Now I can see that I'm actually multiplying those two numbers, and I get 0.05657. So 0.05657 amps. So that's like 56.57 milliamps. So that's the max current. Finally, if I want the total energy, well, that's actually pretty straightforward. I could add this, and what you get is, of course, something that relates Q and L and W and Q and C with sine squared and cosine squared. But if you could get this L in terms of Q, which you can, then you ultimately find out that the total energy is equal to Q0 squared over 2C. But it could also be basically 1/2 L squared I max squared. I'm going to use this because I already have these quantities already written here. So I'm going to say it is 8.0000 times 10 to the negative 7 coulombs squared over 2 times, now my capacitance was 2,000 times 10 to the negative 12 farads. And I'm going to calculate that now. So let's see if we can do it. I'm going to say, again, let's go and grab that number up there already. That's not it. There it is. So I'm going to grab that number, say enter, and I'm going to square it. Then I'm going to divide that number by parentheses 2 times. Now I'm just going to say 2,000 e to the negative 12. And that should give me 0.00016. So 0.0001600 joules are 0.1600 millijoules. That's it. That's what I mean by these types of problems. When I go through and do all this differential equation solving stuff, you should really, by the time you finish the differential equation class, be able to regurgitate these derivations. But right now, this isn't differential equations. This is a physics class. So that's not really the goal for this class. The goal for this class is for you to be able to use the formulas that we've been able to derive from those solutions. So that's what I want you to be able to do for this course, is just be able to apply these formulas. Now we've finished the LC circuits. The next thing I want to do is actually introduce you to the LRC circuit. And this is a special case where instead of actually putting in a power supply, we're going to assume that we initially start with a charge capacitor, just like we did with this circuit. So anybody have any questions on how this problem worked out? I'll go ahead and put it in its entirety right there. Of course, if you need to remind yourself what the problem was, you can always go back and listen to it. But basically what I said was a 2000 picofarad capacitor was fully charged with a 400 volt DC source. And it was then disconnected and reconnected to a 100 millihenry inductor at t equals 0 seconds. I asked you to determine A, the initial charge of the capacitor, B, the period and frequency of oscillation, C, the max current in the circuit, and D, the total energy in the circuit. So that was the actual problem that I assigned to you. So anybody have any questions on anything I did there? So a lot of this stuff, it looks really complicated, but that's because you're maybe not separating out the derivation from the actual formulas. The place where I told you you had to derive stuff is, like I told you, you should be able to use Gauss's or Coulomb's law to find the electric field, use delta V equals a negative integral E dot dl to find the change in voltage from one charged plate or cylinder or sphere to another, and then use C equals Q over V to calculate capacitance. That's the derivation you should be able to do. And then I also said you should be able to use Ampere's law or the law of Biot-Savart to find the magnetic field, and then use the flux formula, phi equals the integral of B dot dA, to find the flux due to that magnetic field, and then finally use L equals N phi over I to compute the inductance. Those are the two real derivations that you got to be able to do, in addition to just using Ampere's law and, of course, Biot-Savart law and Gauss's law and Coulomb's law. All right, so it looks like no one has any questions. I kind of worry about this when everybody's so quiet, because I'm worried that I'm sort of steamrolling you and killing you, and just aren't willing to tell me about it. So anyone? Okay, well, let's start with the next. So we're going to do an LRC circuit. So what I'm going to do is I want you to imagine that we have a capacitor that has a capacitance C. I'm going to also assume that it has an initial charge Q0. Okay, so we can say it's positive, negative, like that. That's going to be connected in series with a resistor of resistance R, and then with an inductor of inductance L, and then it's going to have a switch connected to it, so that the instant I drop that switch, these positive forces or these positive charges are going to be compelled to run towards this negative charge. That's going to, in fact, establish a current around the circuit, and that current I will be negative dq dt, because as the charge Q on the actual capacitor changes in time, a decrease in the charge will result in an increase of the current. Okay, if it wasn't for this resistance, it would just be an LR circuit, or excuse me, an LC circuit, which would go forever sloshing energy back and forth between here and here. But because we actually have a real circuit, it's going to have a resistance, so it's going to degrade over time. So if I go writing Kirchhoff's loop rule, again, this is the derivation part. So it's not the part you're supposed to be able to do until maybe after you have your differential equation class. I think most people could probably do it even after this introduction, but really it's not necessary until you get through your differential equation class. So according to Kirchhoff's loop rule, I'm going to have a voltage increase of Q over C. And then I'm going to have a voltage decrease of I times R. And then I'm going to have another voltage decrease of negative L di dt. And then I get back to where I started from, and I have 0. Now, remember, I is equal to negative L, or excuse me, is equal to negative dq dt. So we can now rewrite this as L. Well, we're too fast. We can write this as L times d2q over dt squared. Notice the sign changed. Plus, now I can write r dq over dt, and I can write plus 1 over c times q is equal to 0. And I think you will see that that looks exactly like m d2x over dt squared plus b dx dt plus k times x, which equals 0. That was the simple harmonic oscillator. Of course, 1 over c takes the role of k, r takes the role of b, and m takes the role of l. So what we get ultimately is a solution q is equal to q0, and this is a very special case I'll mention in a second, q0 e to the negative r over 2l t times cosine omega prime t plus phi for specifically the underdamped case. So underdamped means it's actually going to oscillate. And in order for that to be underdamped, you have to have that r squared is, I think r squared is supposed to be greater than, let me double check this. I think I might have wrote it backwards in my notes. Yes, I did write it backwards in my note. R squared should be less than 4L over C. I'd actually written this backwards in my notes. Glad I caught it before I wrote it down for you guys. So as long as R squared is less than 4L over C, it'll be underdamped, and it'll actually oscillate. So in fact, what the function looks like in that case is, depending on the initial conditions, of course, is it might go like this, where this is an envelope that's given by e to the negative r over 2l times t, and that would be the charge as a function of time. Okay, so that's an oscillatory case. That's the underdamped case. There's also a critically damped, which doesn't mean anything to us. That just means we've made a dumb circuit. And critically damped would imply R is equal to 4L over C. And then there's overdamped. And that means that there's going to be no oscillation either, just like the underdamped. And that's going to be R squared, and this is supposed to be R squared. R squared is greater than 4L over C. Okay, but this solution is only for the overdamped case. Excuse me, the underdamped case. So remember, what happens with the underdamped case is it's kind of neat. Specifically, what happens is you end up getting a I, if you actually use the solution, instead of using the solution Q equals Q0 times cosine, you try to use Q equals Q0 times e to the rho t. And what you'd get is that rho has an imaginary part and a real part because it has a solution that has a negative discriminant. Remember in the quadratic formula, Q squared minus 4AC. If that's negative, then you're going to get an I. When you get an I, you get a exponential that oscillates, but the real part will actually come out here and be multiplied by, so that's why we're getting the damping. Okay. Now, I should also point out that this omega prime is in fact equal to the square root of 1 over LC minus R squared over 4L. So it's a little uglier than it was when we were doing the damped harmonic oscillator, but it's still a decent formula, something we can work with. So this is the equation you need to be able to use And this is another equation you need to be able to use. The initial conditions will give you what phi is and what Q0 is. Like I just showed you in the previous example, you can just calculate it if you wanted. And of course, the data will give you omega. You'll know about R, L, and C, so you can make sure R squared is in fact less than 4L over C, so that you do in fact get a negative under the square root, which is what has to happen for you to get this cosine term. If you get the critically damped term, and you'll learn this in differential equations, the critically damped term becomes a problem, because normally what you get when you plug this, remember I said we'd use Q equals some constant times e to the rho t. Well, you normally get a plus, a row having a positive answer and a row having a negative answer. And those two, e to the rho t and e to the negative rho t, are what we call linearly independent. So they're sufficient. That's a sufficient number of solutions for a second order differential equation. But if you have this being 0, which is what happens when this is equal to that, then when 4L over C is equal to R squared, the row doesn't have a negative part and a positive part. It just has one part that's either negative or positive. So the rules of differential equations say, okay, well, now we try multiplying that by a linear function of t. So we take e to the rho t, whichever row happened to be right, and multiply that by parentheses 1 plus, or a plus b times t. And that actually gives you a solution that is critically damped. Okay. And then the overdamped part is basically you're just going to have those two oscillatory parts basically disappearing, and you've got all decay. Okay. So that's more than you really needed to know, but I'm just sort of tipping my hands at you, or tipping my hand for you to see what comes in differential equations. So with that in mind, let's do an example with this problem. So we're going to take a circuit like this, an LRC circuit, and I'm going to actually try to solve a physics problem with it. Okay, so this is example 2. And what I'm going to say is at t equals 0, we're going to have a 100 millihenry inductor. 100 millihenry inductor is going to be in series with a 5 microfarad, well, with a charged 5.00 microfarad capacitor and a 5 ohm resistor. Okay. What I want is to see if it oscillates. B, I would also like to know, if it does, what is the maximum current? And C, what's the frequency and period? So C, I'm going to say, what is T and F? And then let's say, actually, that's not what I want to do. Is that right? I want to see if the circuit oscillates. That's right. Let me check what it is. I don't think that's what I wanted to do at all. Oh, yeah, I want to determine. Yeah, I want to determine the frequency. Oh, I remember what it was. I'm sorry. I was actually mixing this up with the last problem I just did. Sorry about that. So yeah, first I want to see if it oscillates. I guess you probably can already figure out whether or not it does. Remember, overdamped and critically damped means it does not oscillate, and underdamped means it does oscillate. So I also want to know in part B, I want to know the frequency and period. So that part was still right, but it was part C. So I'm going to say period equals question mark, and frequency equals question mark. Again, that's assuming that it oscillates, as you might suspect it does. C, I want to see how long it takes to drop the charge to half its value. So I want to say T equals question mark when Q is equal to 1/2 Q0. So in other words, I want to see how long it takes to drop the capacitance charge from Q0 to 1/2 Q0. And let me see, do I want to write anything? Oh, okay, yeah, in part D, I want to know how can we adjust R so it will not oscillate. Okay, so that's what I want to do with this one. So first off, whether it oscillates or not means what is R squared compared to 4L over C. Well, R squared, I think you can see, since R is 5 ohms. Sorry about that, that was supposed to be turned off. R squared is 5 ohms squared. So when I square that, I get 25.0. I don't know why I wrote the 5 first, but I did. 25.0 ohms squared. Okay. What's 4L over C? Well, 4L over C would be 4 times L, which is 100.0 times 10 to the negative third henries, over C, which was 5.00 times 10 to the negative 6 farads. And 4 times, basically that's going to be 1, 2, 3, that's going to be 0.1, so that's 0.4 over 5 times 10 to the negative 6 would be 0.12345. So I got to go 5, 1, 2, 3, 4, 5 like that. So that's 1, 2, 3, 4, 5, 6. So yeah, that's that. And henries over farads does actually give me ohms squared. So this is 5 1/millionths. So what that means is basically I'm going to take 4 and multiply it by 1,000,000 and then divide it by 5. Okay, or 0.4 multiplied by 1,000,000. So this will be 400,000 ohms squared divided by 5. And of course, 5 goes into 120 times, so it must go into 480 times. So it'd be 80,000 ohms squared, which is much, much greater than R squared. Okay, so we can say A, it does oscillate. And that's because R squared is less than 4L over C. Does that make sense to everyone? Hopefully I did my math right. I'm just working it out in my head. I had some things come up, didn't let me finish writing out all my notes like I wanted to. Now let's check part B. What is T and F? Well, really F is given by omega prime equals 2 pi F. So F would equal omega prime over 2 pi, and omega prime is equal to the square root of 1 over LC minus, of course, what we found just now was the formula 1 over LC minus R squared over 4L squared. I want to make sure that's right. Hold on. Yeah, that was right. Okay. So I got to calculate that. So omega prime is going to equal square root 1 over L, which was 100 times 10 to the negative third henries, times C, which would be 5.00 times 10 to the negative 6 coulombs, minus, we already know this R squared was 25.0, no, just 10, sorry, ohms squared, over 4 times L squared. So that's 100.0 times 10 to the negative 3 Henries squared. And this should all come out in radians per second, but y'all can verify that if you'd like. So let's calculate this and see what I get. So I'm going to say 1 divided by parentheses 100 e to the negative 3 times 5 e to the negative 6. That's just the first part, so I'll say enter. So this part right here is 2 times 10 to the 6. That's 2 million. I'm going to say minus. Now I'm going to say parenthesis, just to be safe, 25 divided by parenthesis again, 4 times 100 e to the negative 3, and I'm going to square that quantity. Okay, so this is evidently the square root of 1.99938 e to the 6. So times 10 to the 6 with whatever unit. So I take the square root of that. I'm going to say second function square root, second function answer. And that gives me omega prime is 1,413.99 radians per second, which I'm going to say is 1.41. That's 3. That's really how many sig figs you have. So I'm going to do this to carry 1 extra digit, and that's radians per second. So that means F would equal omega over 2 pi. So I'm going to take this number and divide it by parenthesis 2 times 3.14159. And that gives me 235.0. And that's hertz. So that's the frequency of oscillation. And we also want the period. Well, period T is just 1 over F. So I'm going to say 1 divided by answer. And that's going to give me 0.004444, which is actually 1 extra sig fig seconds. So that's going to be 4.44 milliseconds is the period of oscillation. And part C, at what time will Q equal 1/2 Q0? So what we found was Q was equal to, and I'm trying to, actually let me pull back the notes. Q was equal to Q0 times e to the negative r over 2L times T times cosine omega T plus phi, right? Well, this is just going to wobble back and forth between plus and minus 1. This is what's going to make it become 1/2. So if I set 1/2 Q0 equal to just Q0 times e to the negative r over 2L times T, then I should be able to find it that way. So obviously the Q0s cancel out. I take the log of both sides. That's the ln of 1/2 is equal to negative r over 2L times T. So T is going to equal negative 2L over R times the ln of 1/2. Of course, the ln of 1/2 is just negative 0.693. But either way, we can now calculate that T should equal positive 2 times 100 times 10 to the negative 3rd Henries over 5.00 ohms times about 0.693, which I think is what that is. I'm just going to use ln of 2 anyways. but here we go. So 2 times 100 e to the negative 3 divided by 5. That's that multiplier. And now I have to multiply that by the ln of 2. So I'll say times natural log 2. And that gives me 0.02773 seconds, or 27.7 milliseconds is how long it takes. Any questions on that one? Nothing at all. Okay, now part D. Part D is how would we make it not oscillate? Well, if you wanted to not oscillate, then you'd want the R squared to be equal to 4L over C squared, or whatever that condition was. Yeah, 4L over C, excuse me. So I want, since 4L over C is equal to, what did we get? 4L over C, we got something like 80,000 ohms squared. That means R should be equal to the square root of something like 80,000. Again, this is assuming I did my calculation right, but I haven't heard whether anybody's actually verifying any of my calculations. And that one I did do in my head. So just be careful with that. I'm warning you. So I'm going to take the square root of 80,000. And I'm going to get 282.8. So I'll call that 283 ohms. So if I increase the resistance to 283 ohms, it would stop oscillating. And the graph, instead of going like I showed you earlier, the graph at critically damp would just go like that. Whereas underdamp would do a slightly different curve, but not a whole lot different. So that's Q versus T. Any questions on that?
For the frequency equals omega over 2 pi. Is it supposed to be omega prime over 2 pi?
Yeah, it was supposed to be. Sorry. I'm so used to writing omega. Yeah, I wrote it correctly there, but I didn't on the other one. Thanks for paying attention. All right, so the last thing I really want to go over in this chapter is really working with you to work out, for instance, the phase angle and that kind of stuff for an LRC AC circuit. Okay, so let me start by looking at example 30-11, essentially example 30-11. From your textbook, okay? So with that problem, what we're doing is we're considering an LRC circuit. And basically the R is 25 ohms. The L is 30 millihenries. And the C, the capacitance, is 12 microfarads. Okay. And they're connected to a 90-volt AC source. So V AC is equal to 90.0 volts. And that's actually the RMS value. Okay. Now the RMS value just means that basically you can still use the formulas like V equals IR, but if you use V RMS, then this has to be RMS and this has to be RMS. Okay. You could also do it with V peak or peak to peak, and then you just use V peak to peak, I peak to peak, and of course R peak to peak doesn't mean anything, neither does R root mean square. But anyways, the main thing to understand here is we have Eli the Iceman at work. So Eli the Iceman just means E leads I by 90 degrees in an inductor. and I leads E by 90 degrees in a capacitor. That's all that means. So how do we actually implement that? Well, it turns out that basically you have V RMS is equal to I. Remember I said V equals IR? Well, it turns out there's something equivalent to R, but it stands in for R for an inductor or for R for a capacitor, and it's called the reactance. Z is called the reactance. Okay, and it's given a symbol, or excuse me, impedance. Sorry about that. I was jumping ahead of myself. Impedance. Okay, and it's given the symbol Z. So V root mean square equals I root mean square times Z. And you could also write, if you were doing, say, peak to peak, you'd say V's are just plain amplitude. You'd say V0 is equal to I0 times Z. That will work as well, okay? But when you're talking about an inductor, you would say V, oh, wrote an L there by mistake. If I'm talking about an inductor, I'd say VL0, meaning the amplitude is equal to the amplitude of the current times what we call the XL, which is the reactance that I was talking about earlier. Okay, so that's the reactance of an inductor, but you could also say the capacitance amplitude is equal to I amplitude, and in this time it's times the XC, which is the reactance. So these two are reactants. Okay, and the Z is the impedance. Now, what's that mean? Well, all that means really is that there's a quantity equivalent to resistance. It's even measured in ohms, but it has a weird quality to it in that it's actually frequency dependent. So, for instance, one way we can deal with this Eli the Iceman thing is we can say, okay, well, XC, that's the capacitive reactance. That XC has to be represented, or has to represent the idea that in a capacitor, the voltage lags behind the current. And if you look at a phasor diagram, for instance, you'll see that it's actually behind. And the way they do that is they realize, well, normally what we do is we'd say negative I over omega C is it. Okay, that negative I seems weird, and your book doesn't discuss it this way, but I like it, and I will explain it this way in a second. What you can do is alternatively, you can forget about the imaginary number and just say XC equals 1 over omega C. What that tells you is as the frequency, which remember frequency is F, and then the angular frequency is 2 pi times F, so that's omega. So in other words, when frequency goes up, omega goes up. But you see larger and larger the frequency gets, the less and less resistance a capacitor becomes. It's like taking the limit as x approaches infinity of 1 over x, right? And then they also say, well, XL, the inductive reactance, is actually equal to I times omega L, which alternatively, you could just say XL is equal to omega L, and that's what your book's doing, okay? I'll show you why we choose to do it that way, okay, in a second. So what we're actually going to do in this LRC circuit is we're going to draw a phasor diagram. So what we're going to do is we're going to imagine a X and Y axes, or axis, if you will. Let's call this X. And I'm going to say this part's real, okay, because that helps me with the I. And I'm going to say this part is imaginary. Okay. Now, what we have is after any time t, this phasor diagram has rotated by an angle theta equals omega t. Okay. Now, this quantity right here is, in fact, you could interpret it a couple ways. One, you could, let me do a different color. I'm going to do that to represent I0. So that's the actual amplitude. If you made a graph of I versus t, and it looks something like this, okay, that's I0, and this is negative I0. So that's all that means, is that little thing there is I0. But this quantity right here, this whole length, is VR0, which equals I0 times just the resistance. Now I'm going to put 90 degrees in front of that. I'm going to put another quantity, and that's going to be VL0, which of course is I0 times XL. And then 90 degrees behind that, I'm going to put another quantity, VC0, and that's equal to I0 times XC. So if you're treating this vertical axis as imaginary, then any number on here, like 1, is technically 1I, 2I. So this might be 1I, 2I, 3I, 4I, and this might be negative 1I, negative 2I, so on and so forth. So you can see now, if I did that, that negative I times omega c literally puts this down here on the bottom. So it takes care of the Eli the Iceman problem all on its own. If you want to know the voltage at any particular time across any particular device, you just find its component on the real axis. So this is VL as a function of time. And obviously that would be negative in that case. This would be VC as a function of time. And this would be VR as a function of time. So we just allow this vector right here to rotate around at an angular frequency of omega. And at any point in time, we can just do the projection about it. Okay, thanks. Appreciate that, Cadmium. All right, so now all we have to do now is to figure out really how far away, because what's going to happen is now we're going to get a voltage vector that adds these quantities and is sort of the voltage as a function of time, if you will. So that's just plain, let's call it, say, V0. Okay. Well, it turns out that V0, and keep it in red now, V0 is actually equal to the square root. Notice this is just like adding vectors. So this is a vector. This is a vector that's 90 degrees behind it. This is a vector that's 90 degrees in front of it. So these two fight one another to make a y component, if you will. Notice in this case, this one's longer, so it's going to actually win a little bit. And then this amount right here would actually be VL0 minus VC0. And this amount right here is just going to be VI0R, or VR0. So ultimately what we get is VR0 squared plus VL0 minus VC0 squared, which becomes I times the square root of R squared plus XL minus XC squared. And you get ultimately the impedance, which the impedance really matches sort of the net resistance of the whole circuit. even though it's is actually frequency dependent and that sort of thing, you end up getting, if you want V0 to equal I0 times some quantity like Ohm's law, then your answer is Z. So you get V0 equals I0 times Z, and Z would have to be defined to be the square root of R squared plus, now here's where you can sort of ignore the i's. There's ways of dealing with it, but we can ignore the i's. We just say omega L minus 1 over omega C squared, like that. So then all we need is to find out exactly what is this phi, what is this angle right here, phi, called the phase angle. So let's do that. We want to know phi and we want to know V0. So that's our problem. V0 equals question mark and phi equals question mark. And of course, you can also say that Z equals question mark. So if I want to do that, first off, I'm going to calculate XL. So I'm going to calculate XL is equal to, again, when I'm talking about magnitudes, I just throw away the I. The I is just there, and the negative for that matter is just there to make sure that it lags in the case of XC, and that it goes ahead in the case of XL. So I'm just going to say XL is, of course, omega L. So we're going to say, oh yeah, I forgot to put the frequency. I think we were using 60 hertz on that example. No, it's 500 hertz. Whew, really missed that one. And F is equal to 500 hertz. Okay, so that's the extra part that I'd forgotten to include. F is equal to 500 hertz. So now I'm going to say omega is 2 pi F. So 2 pi times 500 hertz times L, which we said was 30.0 times 10 to the negative third henries. And obviously this is going to give me units of ohms. So 2 times 3.14159 times 500 times 30 e to the negative 3 gives me 94.25 ohms. Okay, so that's the first part. That's the impedance of the inductor. Now I'm going to do XC, which equals 1 over omega C, which is 1 over 2 pi times 500 hertz times the capacitance, which was 12.0 times 10 to the negative 6 farads. So I'm going to do 1 divided by parentheses 2 times 3.14159 times 500 times 12 e to the negative 6. And that gives me 26.53 ohms, again, carrying 1 extra sig fig. Now I can find the total impedance. Z is equal to square root R squared plus XL minus XC squared. So I'm going to say square root of 25.0 ohms squared plus 94.25 ohms minus 26.53 ohms squared. And that's going to give me, first off, I'll say square root 25 squared plus parentheses inner minus parenthesis minus this guy 26.528 inner, and I'll square that thing, and that gives me 72.19 ohms. Okay. Now, if I want to know IRMS, well, I RMS, which I didn't ask for, but I meant to. Okay, so if I want to know IRMS, I'm just going to take VRMS and divide it by Z, because you could do it with the amplitude or the RMS. So I'm going to take the 90.0 volts and divide it by 72.19 ohms. And that'd give me 1.247 amps. Okay, so about 1.25 amps. If I wanted to know the phase angle, and I do, there's a couple different ways. I'm going to take cosine phi is actually equal to R over Z, because that way I like a little easier. That means phi would be the inverse cosine of R, which we found was what, 25.0, over Z, which we found to be 72.19. So I'm going to do trig function cosine inverse of 25. Notice I am in degree mode, of 25 divided by 72.19. And that gives me 69.74 degrees. Okay. If I wanted to know the voltage, root mean square voltage across the resistor, I could then say V RMS for the resistor would equal I RMS times R. And you can do this yourself to make sure, but it's basically 31.2 volts. V RMS across the inductor is I RMS times XL. In that case, you get 118 volts. And finally, VRMS across the capacitor is IRMS times XC, which you can see is 33.1 volts. And that's it. That's sort of the crux of all the possible problems that we could really ask you regarding this stuff. You don't need to know these derivations. You don't need to. I'm not studying resonance. I'm not doing impedance matching. And I'm not really going to talk about three-phase AC, but if you're planning on doing anything with electrical, you should definitely read as a bare minimum resonance and three-phase AC, because three-phase AC is actually how our power grid runs here in the US. I assume it does in the same way in Great Britain, but I've never been there and haven't read about it being triphasic or not. So anybody have any questions?
Yes, for XL, we had omega times capacitance, right? And I think we put the inductance instead of the capacitance in the equation.
So when I was doing this, you think I might have used the...
It's up on XL equals 2 pi times 500, and it's 30 times 10 to the negative third henries, but I think it's supposed to be 12.0 microfarads, right, for C, for capacitance.
Yeah, that was supposed to be 12. Nice catch.
And I think that messed up the XL value or XC value too, because then it's 1 over that value, right?
Right. Actually, I was just looking. I think you might have misread my L for a C. In fact, let's check, because I more or less stuck to the same problem from the book. Let's see what the book values had. Turning to page 801. It had XLs equal to 94.2. Okay, I got the same thing. Yeah, so I think you might have just misread what I did. That is the right value there. And then if I look at XC, they got 26.5. So did I. So that's good. So yeah, it's good that you were paying attention, but it might have just been my C's and L's look alike.
Oh yeah, I thought that was a C, but it's it's an L.
Yeah, that's cool. Nice catch. I appreciate you paying attention to that.
All right, thank you.
All right, well, that's it, guys. Time's up, and you all are free to go. Please try to read chapter 31 for next time. That way we can sort of just skim it kind of quickly. I want to talk more about the big concept ideas of that so that we don't have to do so much stuff. But you guys are free to go. I'll wait for the last one to leave, and y'all have a good one, and I'll see you next week. All right, looks like that's it.